So we're going to be talking about exponential functions today. Now, an exponential function looks like this. F of x equals a to the x. So basically, one where you have a number, a constant, raised to a variable. So for example, f of x is equal to 3 over x, 3 to the power of x. F of x is equal to 1/2 to the power of x. Okay, so the base is a number, the exponent is a variable. Now, I have a little secret for you. Don't share this with anybody, okay? The domain for all exponential functions is always all reals, okay? So, domain, always all reals. Don't tell anybody, okay? So, look at this one, 2 to the x. Is that an exponential function? Yes. So what's the domain? So these are your free points. Okay? Now, another thing about exponential functions is they all have horizontal asymptotes. Yeah? Yeah. So they all have horizontal asymptotes. The default is that the horizontal asymptote is at x equals 0. So now we're going to graph this, and you know what? We're going to put it in the calculator. Okay? And that's what it looks like. Okay? Now, if I want to reproduce this on my graph, my easy way of doing it is I press trace. I already have a point there. When x is 0, y is 1. Now in trace mode, I press 1, enter. When x is 1, y is 2. And then I, just give it another number, like x is 2, y is 4. Okay? And go ahead and label those, 2, 4. 1, 2, okay? When it does say specifically to label 2 points or 3 points, you are going to have to label them. Now, for the range, okay? You see here that the graph starts at y is 0 and goes up. Now, what's the deal with an asymptote? What is an asymptote? Exactly. An asymptote is a line that the graph comes exceedingly close to but never touches. Okay? So, the graph starts at 0 and goes to infinity. It never hits 0, so it's an open parenthesis. Okay? All right. So that's that. Now, look at this one. I have 2 to the x plus 3. The same graph as before, the same equation as before, with the addition of plus 3, and I can already see some of you guys motioning and saying that this is going to be a shift 3 units up. Everything about the graph shifts, including the asymptote. Okay? And if you were to graph 2 to the x plus 3, you'll see that that's exactly what just happened. Okay? We're going to label the points as before. So here, here, here. Okay, so when x equals 2, trace. When x equals 2, this time around we're at 7. Okay? So what's the domain? Now what's the range? And I'll take your question. 3 to infinity. Okay? Okay, so we have some exponents with, we have some rules for exponents. If you have a to the x times a to the y, you add the exponents. So it becomes a x plus y. Okay? If you're dividing, like in number 2, you subtract them. Okay? If it's a to the x to the power of y, you multiply them, a to the power of xy. Okay? If it's something like this, where the bases are different, but the exponents are the same, what you can do is you can combine them, so it's ab quantity to the power of x. Because this goes backwards. Okay? So basically, if you had what I just wrote down, and you wanted to expand it, what would you do? You would give an exponent to the a, you would give an exponent to the b. So it would be a to the x, b to the x. Okay? So, like in this next one, for example, if you have a quantity raised to the power of exponents, you distribute a to the x over b to the x. Good. Okay? Now, use a graph to find the zeros of the function, and it says to use a graphing calculator. So let's use a graphing calculator. Basically, I want you to be practicing with the zero function. So 3 to the x minus 4. We're going to graph. Now, to find the zeros, I do second calc. And which option? 2 for 0. Now it asks for a left bound. So what I do, this is my fail-safe way. I go to the point. So the 0 is that point, right? My cursor is now on the 0. So I bring my cursor to the point that I'm trying to locate. Then, when it asks for left bound, I just press the left arrow a couple of times. Press enter. Now, right bound. Bring the cursor to the point, go to the right of it a couple of times, press enter. And it's right there.
So the 0 is when it crosses the x-axis?
Yes. Okay? So, the 0 is 1.26, comma, 0. So this is partly notation. That's how I want you to do it. All right, let's do that again. Second calc, 0. Now, it wants the left bound. So I bring my cursor to the point that I'm trying to locate. And then if it wants left bound, I just press the left arrow a couple of times, press enter. Now it wants for right bound. I take it to the point I'm looking for, press the right button a couple of times, press enter. If you did it correctly, the arrows here have to be pointing at each other. Okay? Now it asks, do you want me to guess? And you say, press enter. Sure, knock yourself out. There it is.
So,
Yeah.
regardless of how many times you go to each side,
Doesn't matter.
you'll still get the same
Yeah.
answer?
So let's do this one. 2 e 2e to the x minus 5. Oh. All right. So again, second calc, 0. Now, it wants left bound. So first, take the cursor to the point you're trying to locate. Now, press the left arrow a couple of times. 2 times, 3 times, doesn't matter. Enter. Then, take it to the point again, and then press the right arrow a couple of times. Enter. You want me to guess? Knock yourself out. So there it is. 0.920. Okay? What do you mean? Okay, now, I'll tell you guys. Let me finish this and I'll tell you guys. Okay, so exponential growth and decay. So the functions look like this. So you have a constant times something to the power of x. So for example, you could have like y equals 3 times 2 to the x. You could have y equals negative 5 times e to the x. These are all examples of exponential growth and decay. Now, the thing with exponential growth and decay is change happens very quickly. So look at this graph, for example. All of a sudden, it just shoots upward. All right? So an exponential growth, it's like you are feeling just fine, and then somebody, your friend is sick, they have like strep throat, they cough next to you, and within hours, you're just like, you're shut down. Okay? That's exponential growth because that bacteria multiplied exponentially. And then you take antibiotics, and within hours, you're feeling so much better. That's exponential decay. Okay? Now, the equations look the same with one difference. It's exponential growth if a is greater than 1. So if the number that's being raised to the exponent is greater than 1, it's exponential growth. So y equals 2 to the x, y equals 5 over 3 to the x are all exponential growth. Y equals negative 5 over 3 to the x, also exponential growth. You ignore the negative. Okay? Exponential decay is if a is between 0 and 1. Y equals half to the x. Y equals 1/3 to the x. Negative 1/3 to the x. What if you have y? It's still growth. It's just growing into the negative numbers. So if it's negative, it looks like this. So as you move further and further, it's going closer and closer to 0. Okay.
Is the range not between 0 and 1?
Not the range. This value, this number.
That number.
That number.
Negative 1/3.
Yeah. You ignore the sign. Yeah.
Is the reason that then negative 1/3 x is exponential decay and not growth is because it's outside of it's because there's no parentheses around it.
Right. Whether there was parentheses or not, you would ignore the negative. So really, this should say absolute value of a.
But then how does that differ from exponential growth where there's the parentheses 5 over 3?
Well, 5 over 3 is a number that's greater than 1.
Okay.
Yeah, 1 over 3 is a number that's less than 1.
So it doesn't matter. So regardless, you don't think about the negative. You think about
Yes.
the actual number.
Absolutely. So this would also be the same.
So if it were negative 2, it would still be an exponential growth.
Right.
Okay.
Now, what if you had this? Y equals e to the negative x. This time, where is the negative? It's in the exponent. And what do we know about negative exponents? What do they do? Okay, so if you have, it goes to the denominator. So if you have e to the negative x, that's the same as 1 over e to the x. Okay? 1 over e to the x. So now that is decay. Why? Because another way I can write that is 1 over e to the x.
How do you know what E is?
E is 2.7.
Oh.
It's a constant like pi. E is a constant 2.7.
So if you did like 1 over 2.7, it'd be more.
It'd be less than,
1.
yeah.
Yeah.
So let me do another one. Suppose you have y equals 3 to the negative x. Because there is a negative exponent, that's the same as 1 over 3 to the x. And that's the same as 1 over 3 to the power of x. Okay?
So this would be
Decay. All decay. So when the negative is in the exponent, decay. Yeah.
If it's negative in the exponent, so if it's negative in the exponent, it's growth. And if it's negative, or if it's negative in the exponent, it's decay. If it's negative in the base, it's growth.
It doesn't matter. If it's negative in the base, it could be growth or decay. If it's, guys, listen. If you're looking at the base, you ignore the negative altogether. So in this case, I take whether 5 over 3 or negative 5 over 3, they're the same. So when you're looking at the base to see if it's greater than 1, you ignore the negative altogether. The only time that the negative cannot be ignored is if it's in the if it's in the exponent. Okay?
Which is the way to go.
Right. Okay, so now let's see if we can match some of these. So let's look at this first equation. 3 to the x minus 2. Now what does that minus 2 do? Moves it down 2. So which one do you think? C. We're matching, yeah. So now you have 3 to the x. Now would you say that's growth or decay? Growth. So we already used C. Which one of these looks like it's growth? A. Now, okay, so 3 has way too many negatives. Why don't we go to 4? 1 over 3 to the x. Does that look like it's growth or decay? Decay, so which one would you say? B or D? I couldn't hear you. B. So that must mean this is D.
So because it's negative, it's going negative. Is it because the exponent,
So
is it because x is negative?
this negative makes it below the x-axis. This negative makes it approach the zeros.
so it's exponential growth.
Decay.
So will something like that be able to match it?
Maybe.
Wait, next one.
If, as you approach the right side of the graph, if your graph is approaching 0, it's decay. Like you see here, it's approaching 0, it's decay. If on the right side of the grid, it's going up away from 0, or it's going down away from 0, then it's growth. Okay? So if it's going away from 0, it's growth. Okay. Now,
It starts at 0 and then goes down like negative.
so
Which one would
it won't start at 0 because that won't be an exponential function. It would have to start from,
like if it
the
starts
far
at, like,
left end.
1 and then goes down.
it's going away from 0, it's growth.
Okay. That's interesting.
Yeah. Yeah.
Then in what case would it be?
Like if your debt is increasing.
Oh, okay.
Okay. Yeah. Okay, so speaking of the number E, so many phenomena are modeled by exponential functions. And their base is this famous E. And it's named E. It's called E after the mathematician Euler. Euler. That's how you pronounce that. Euler. Okay? So E is like pi. Many people call it different things, and they're wrong. It's Euler. So E is an irrational number. E is an irrational constant like pi. And to, the first several decimal places, that's what it is. Basically, it's 2.7 for all intents and purposes. Okay? In Algebra 2, we actually touch on how this comes up. It's not super, super important right now. Okay? Now, this also comes up in algebra, compounded continuously. So, if you have money invested in a bank account, okay, we know this formula, we call it APERT. So, A is the balance in the account after several years. T is time in years. P is the initial investment, it's how much you go to the bank with. And R is the rate. Now, take that, A equals PE to the RT. And what if I just write the same formula with different letters? Instead of A, I write Y. Instead of P, I write this funny Y0. E is constant, it stays. R will switch for K. T, I'll just leave it. I'm done changing things. Have I changed the formula? No, I've just changed the symbols.
Why do we need both?
Okay, so APERT is, it's got symbols that have been modified to reflect vocabulary in the banking world. But that's only 1% of the real world. Everything else that we deal with uses that purple general formula. Now, that Y with the subscript 0, we call it Y naught. And it's initial. Okay, it means initial. So, Y is the amount after time t. Y naught is the initial amount. K is the rate of change. So, same situation. All right. So the population in a town in 2000 was 56,000, and it's increasing at a rate of 2.5%. So now, the 56,000, this is when the problem began. So that's our initial amount. What symbol will it get?
Why not?
Why not? The rate is 0.025, but we're not going to call it R actually, we're going to call it K. Now it says to estimate the population in the year 2020. So let's write down what we have. Y naught is 56,000. K, 0.025. T, 20. So Y is equal to 56, Y naught e to the KT. 56,000 e to the 0.025 times 20. Now, let's plug it in. So it's 56,000 e to the power of 0.25 times 20. Oh, sorry.
We're not gonna like end up with logs and stuff when we do this in like LN.
Hang on. So here we go. So what? And I'll answer your question. Just let me do this. 92,328. We're not going to do 0.4 because there are not going to be 0.4 people, okay? All right. When will the population reach 75,000? Yeah.
So then you're gonna leave T.
Uh-huh.
And then Y is gonna be 75.
Exactly. So now Y is 75. So there is your log. Equals 56,000 e to the K, K is 0.025. T. So now, first, let's divide by 56,000. So 75 over 56 is equal to e to the 0.025 t. How do I get rid of the e? Using an ln. So I take an ln of both sides. So I have ln 75 over 56 equal to 0.025 t. Now what am I going to do? Divide everything by 0.025. So t is equal to ln of 75 over 56, all divided by 0.025.
Is it always LN, never log?
Yes, for E it's always ln. So, did you already do it?
Yeah, I got
It would be
11.6.
12.
So you get 12, so you can add up to 12.
Okay, so it's 11, okay. So, on the quiz, I will have specified where to round. If it says to round to the nearest tenth, then this. If it says to round to the nearest year, then you will round it to 12 years.
You round to the what?
If it says to round to the nearest year, then say 12. It'll specify. Now, one more. Last one. How much time is required for an investment to triple if interest is earned at the rate of 5% compounded continuously? So, all I have to go on is that interest is 0.05. Now we're talking about interest. So let me just write down the formula before I get too freaked out.
Wait, so interest is always A plus B.
Doesn't matter if we.
Right. No, doesn't matter. Now, I don't know what I'm starting with. I don't know what I'm ending with. All I know is that I want it to triple. So basically, P is my initial amount. So if I start with P dollars, how much do I want to end with? 3P. Okay? So final amount and initial amount. If my initial amount is P, then my final amount has to be 3P because it has to be tripling. So for my initial amount, I'm going to put P. For my final amount, which is A, I'm going to write 3P equal to P e to the 0.05 t. And beautifully, the p's go away. So I have 3 equals e to the 0.05 t. Take an ln of both sides. So ln of 3 equals 0.05 t. Now, so t is ln of 3 over 0.05. And how much is that? 22 years? Oh, okay, let's see. So, ln of 3, parentheses matter. So about 22 years. Now, this homework is due tomorrow.